we are going to continue the lecture, the relational algebra. It was due the last Friday, page 2, including the conceptual design. So on Wednesday, I'm going to have the presentation for each group and for each individual team. Okay, so you don't have to prepare the formal presentation, but it's also a good idea to make the 2 or 3 pages of the PPT file, then introduce what is your project, the problem definition. Even though we are doing the same topic, but the details is different. So why don't you list and explain your problem? You don't have to list up all the query or so on, but you can show the 2, 3 the important query, then in English, then the conceptual level design. That's supposed to be the ER diagram. Then explain the what is your the database gonna be. Okay. So each team or each individual may have the 5 minutes, less than 5 minutes. It's just the sharing your the result or experience with the others. Then the GA, Divya, and me will give the comment if needed. Okay. It will not be graded, but maybe affected your the page 2 grade. Okay. So please, you don't have too much serious, but please be ready. Also for easy transition. So I don't think it works very well to use your laptop. So if you are going to use your laptop, please check your connection before class begins. Okay. So right now the HMI doesn't work very well. Okay. So I think the best idea is if you are preparing the PPT file, upload to your Google Drive. Okay, then use my laptop to log on the Google Drive or Google Slide. That is the safe way. Okay, or if you really want yours, so you can bring the memory stick. Okay, but I don't recommend to use your laptop to change and set up everything. It takes a longer time than expected. Okay, I think the best way is using the cloud, the computing resource for your presentation or memory stick. So each team can have the 5 minutes to introduce your project. Okay, that will be helpful for the rest of the semester to not for better the quality. Okay, so any question? So we may have the 5 teams in classroom, so it may take the 20 minutes, 25 minutes, then we will continue. It is scheduled the C-Corp, the exercise lab, but I don't think we have a time, so we will delay the lab to the next week. So, but please be ready for your MySQL database. We will have the more intensive exercise lab next and the week after. Okay, so last class we start the relational algebra and the relational algebra expression. Some of the students are curious. So do I need to know the relational algebra? So without the understanding relational algebra or relational calculus, you are able to use the SQL. However, as I mentioned at the beginning of the semester, I'm not going to teach details of the SQL. I think that you'd better take the online class or the YouTube or Udacity and for better the instructional material for if you are interested in the only SQL. Instead, who knows? So like think about the language. So we are using English, but the English is not the only language, which is one of the popular languages, but that's not the only languages. Also think about your programming language. So I have used the C or C, Fortran and COBOL when I learned the introduction to computing first time 30, 40 years ago. But 20 years ago, when I started my PhD, also when I started the job at UB, we have used the Java mostly. If you know Java, you can easily get a job. And also for the network, it was a Cisco or something like that. But nowadays, the most popular language is Python and the functional language like that. So such changes. And the SQL is not permanent. However, if we know how SQL was invented, okay, then if you have a chance to know about learn the new language, new database language, or the new program language, or new structured language, it will be easier if we understand the fundamental theoretical approach of how we can create, how we can invent a new language. So it's kind of such a process to know about the fundamental of the new program language. Dr. E.F. Goddard did not propose the sequence select from where. He didn't know that. Instead, he provided the mathematical, the foundation of how to use relation set. Okay? Then somebody implement his idea, that which is sequence structured query language as a programming language, as a software. So because of that, the sequence is easy. The reason is that it starts from the very strong mathematical background. It's not like the intuitive, the program language. Instead, it's a really mathematical, the strong, the background and foundation, such a the program language. Because of that, it's a reliable, doable, and easy to use. So that is the main focus. So also, if you are interested in the further study, like the PhD or the master, so you cannot propose this is my new program language. Instead, when you propose your new idea, so what is our operation? Why? And it's kind of mathematical approach. So you need to prove your idea if you are doing such a research. So last class, before that, we define the relation. So relation is kind of tablet style. We have number of attributes. So when we define the A relation, it's a set of attributes, A1 to AN, set of attributes. It's called the schema. Or if we define the relation, it's a set of the tuple or data or sometimes row, like that. So that is this group of data, group of element is a set in the mathematics. So based on that idea, so we are going to access such a relation in this way. I'm interested in a number of the tuple which has something condition. So at that time we can use selection operation. So selection operation limit the number of tuple which has a specific condition. So we can put such a condition over here. So this is one operation proposed by Dr. E.F. So if a user wants to access a relation, you can use the selection operation, sigma operation with the condition. It's kind of filtering. Okay? Then I'm interested to access specific attribute. Similarly, we can specify this is called the projection. So projection with list of attributes. So we can list of attributes to access specific the attribute over here. Oh, by the way, so this is the selection, and this is a projection, and this is a input is relation, input is also relation. So any operation, relational algebra operation has an input as a relation. Also output is also relation. So because of that, sometimes we can rename. So this is a rename of the relation. You can rename the relation. Also, we can rename specific attribute with which is called the row. It's a relation. It's a rename of attribute. We can the new attribute name. Okay. So this is what we covered last week. And also one more thing is not just only using one operation. We can combine the several operation. For example, we can access the employee whose salary is bigger than 50K, like this. So, whose salary is over 50K will be returned, like this. So, this is also relation. So, we can use the output of this one as an input of projection. I need first name, last name, like this. Okay. This is also possible. This is called relational algebra expression. So this is just one operation, relational operation, but we can create the relational algebra expression as if you create the sentence by combining the several vocabulary with the proper grammar. So with the proper grammar, we can combine, integrate the several operations. Yes?
Sigma means select.
Select.
What does big pi mean?
So pi means project. So we try to access a specific attribute, first name and last name. So with the example, so if you select the employee with the salary, so this will be output, first name, last name, and middle name initial, and the address and salary, all attribute and their information, like the Lee, like the I, and the address is 57, and James Smith, and all information. All attribute will be returned whose salary is bigger than 50K. But I don't want all attribute. So I try to project only first name and last name only. So this projection limit by attribute. So only this, the information will be written.
So it's like a condition.
Yes. This is a condition, this is a list.
List, okay.
Yeah.
Thank
Then, so I don't want the name of this attribute. As a default, original attribute name will be used. So I like to use, instead of the F name, I like to use Fn. The L name, I like to use Ln. So you can rename corresponding. Okay? So you need to follow the same order as the input attribute. Then rename, like this. Okay? Then final output will be like the result. This is the relation using rename. Okay? So this is the called the relational algebra expression. So our goal is to create such a relational algebra expression. It's kind of a composition by following such a rule. Okay, this is what we covered. So if you see their input are how many relation as an input? How many relation? One input, one input, one input, one input. So these operations are called the unary the operation. Unary means one. Okay? On the other hand, because we have a unary, we have binary operation. So binary operation has two attributes, two relation as the input. So we are going to today see such a binary operation. So to do that, let's go back to our elementary school, the mathematics. Once we learned what is a set. So set is group of element, group of number, like that. So we learned there are two sets like this, A and B. So then we learn such a operation. This is called union. Intersection. Intersection means common element will be written. Using Venn diagram, the intersection is like this. Right? And also we learn union is either A or B. And also we learn minus. Minus is A but not in B. Okay? So that is this part. So we can use borrow because our relation is actually from set, which means any operation, any characteristic, any the theorem or the tools used in set, we can borrow. So that is actually another benefit of relational model. Relational model does not propose a brand new idea. Instead, use the existing idea of the set. So we can use such a set operation. So as you can see, set operation input is 1, 2, 1, 2, 1, 2. So this is called binary operation. One more thing. We have seen this kind of operation before. This is called, do you remember in math? Cartesian product. Cartesian product is all possible combination. It's not easy to represent using the Venn diagram. So A times, it's not times A, Cartesian product with the B is all combination of elements. We will see. So we are going to adapt such a set operation to the relational algebra expression. So let me use to speed up a little bit the slide. So union operation. So union student and the instructor. We have the student relation. Student relation has how many? In this case, the 2 attributes and their value. And instructor has F name and the L name, so their value. So we'd like to the union. The first question. Student has Fn, Ln. The instructor has F name, L name. Do they have to be the same name or not? Name is not critical, not important. Instead, domain should be the same, right? In other words, in terms of data structure concept, this is called type comparability. Type comparable. So, for example, character is 1 byte, and the string is 0 byte. But we can the string because character can be string, so we can automatically change the data type. So it's a type comparability using the auto casting. So you can apply the casting. Sometimes yes, sometimes you cannot use such a casting. So if you can apply such an auto casting of the data type, in other words, the same domain. So you can see that this is Susan, Lames, so on. This is the first name domain. And the F name, even though name is different, the attribute name is different, the John, the Ricardo, Susan is from the same domain. It's the same meaning. So in case they are type comparable means the same domain, we can apply this, the set operation. If not, we cannot. Okay? So name is, even we can apply actually Fn, the rename. So we can make the same name. So it's not a problem. So name is not important, instead whether they are in same domain or not. So in this case, it's a Fn, F name, same domain. Ln, L name, same domain. So we can union. So we'd like to union, then it's all the value. Can you find any interesting stuff? Same names? Names are same. Which means So let's take a look at the student. How many students? 7. How many instructors? 5. So if you combine, how many? It's supposed to be 12. 7 plus 5. 12. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So only 10. Why? Same name, duplicate name. Whose name is duplicate? Susan Yao, right? Ramesh Shah. Oh yeah. So we have the 2. 1, 2, 3, 4, 5, 6, 7. 1, 2, 12. And this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2 of them are duplicate. Then, if we go back to the relational definition of a relation, does it allow the duplicate data or not? It's not. Entity, the constraint, okay? The primary key constraint, primary means non-null and unique. So each relation should have one primary key. Primary key is non-null and the unique. So we should follow that the definition so we can automatically remove the duplicate data. However, later when we talk about the SQL, structured query language, even though SQL use the relational algebra idea, but it's slightly different. So I will show you the difference to deal with the duplicate data. But in the relational algebra operation, any duplicate data will be eliminated. Okay, that's the reason we have only the 10. What about the intersection? The union. This one is union. It's the intersection. It's a typo. Okay. So intersection, student intersection with the instructor. So 2 of them will be returned because these are the common instances. We don't have to worry about duplicate data because it's finding the common data. But we need to consider the type compatibility. So from the same domain. What if here instructor has one more attribute, middle name initial. Middle name initial. Suppose that the instructor has a middle name initial. Can we union or not? No. Because the middle name initial domain is not here. So we cannot do that. Okay? So type compatibility means the same number of attributes. Each attribute should be same domain. Okay? So what of the minus? Minus we can take out from the student. It's existing in the student but not in instructor. It's a vice versa. It's in instructor but not in student. So this is the set operation. Okay, so type compatibility means so it should be the same number of attributes and from the same domain. Okay, and I think that we can. You have learned this kind of the things, right? So we can apply all such the set theory into the relational algebra, the operation like the commutative rule. Commutative means you can change the order, right? But you cannot change the order of the minus. Everybody knows that. And it's the same thing in the database, the relational algebra. And also we can do the, what is the name of this rule? Associative. So associative, so you can combine the parentheses, this and this is, doesn't matter. You can do this one. But it's not commutative for the minus operation. Okay, then Cartesian product is all combination. Okay, so let's see the example of such a Cartesian product. I'd like to simplify the student as the and the instructor like this. So we have two relations and two attributes for each relation. So student, Cartesian product, instructor. First thing is the attribute. When you Cartesian product, attribute will be just combined, which means F n, L n, S n, F n. This time, if name are conflict, you can change the name if you want, or we can use dot notation. Relation dot attribute. So you can use the instructor dot Fn, or you can rename if you want. Okay. Then this is our Cartesian product relation attribute. Then what about the tuple? Tuple is all combination, which means it's the same as the Cartesian product that you know. So like this one, A1, A2, all combination, similar way. So for this, we can combine with this, combine with this, combine with this, combine with this. That means A, B, 1, 1, 1, C. A, B, 1, 1, 2, D. C, D, C, D, 1, 1, 1, 1, 1, 1, C. C, D, C, D, 1, 1, 2, D. Like this. So this is the Cartesian product. If you have 1, 1, 1, 1, 3, F, so A, B, 1, 1, 3, F. A, B, C, D, 1, 1, 3, F. So you can have the 2 times 3. So number of the number of tuples of the Cartesian product is number of student times number of instructor. So it's total 6. Cartesian product is a very important operation in relational algebra. Anyone who can guess why this one is the really important? Anyone? So think about the database model, database design. We are doing database design. So relational database model is dealing with what? Very large data. So what's the idea of very large to deal with very large data?
For each student, we can search everything here, so that we can find relation between one student and entire
So
transportation.
in this case,
Yeah.
That's one idea. Then let's go back to the original idea of the relational model. So we are dealing with the big data. How to deal with the big data? Standardize, right? Which means we try to put all student information in student relation. Let's think about regard. Relation is a room. So this room is only for the student. So we can search the student very easily because each student has the primary key, UBID. So using ID, we can search. But I'd like to know about the course taken by student. But course information is not here, relational model. Because we try to standardize the course information in another room. So there's another room for the course only. How can you access student information together with the course information? You need to visit this room, then check the another room. You need to combine two relation, two room. This one, can you combine? It's a unary operation. There is no way. You can access only one room. But if we are using this one, A, B, A, so it's just combine, just merge, or just separate. So no specific. However, if we use the Cartesian product, right? So we can integrate the two different information, two different relation, two different sources. Because we separate. So eventually when we access the data, we need to integrate. That is the the Cartesian product. However,
Additionally, wrong information.
wrong every combination. What we are interested in, let's think about the Fn is the primary key. Okay? So using A, I'd like to find the A. So there's no A instructor. But using C, there exists a C. Their social security number is 111. So what I want is here, where is that? A, B, C, D, this is a C, this one, right? So what we want among the all combination of the data, what we want is only this one. How can you find this?
Before using the product, we have to filter out.
Filter. Do we have any operation regarding to the filter? Which one? Which one?
Sigma.
Sigma, selection. So, what if this one? So, student, Cartesian product, instructor. Okay? Then, what we want is selection, what? Student F name is equal to, we want this one, and this one is the same. Instructor Fn. Once again, so using Cartesian product, we can find the all combination, but it's too long. It's everything. We don't want everything. Instead, it's a matched one. Okay, we need to filter such a matched one. What is a matching condition? F name is equal to F name. S dot F name is equal to I dot Fn. Then only this, the tuple, will be returned. Then finally we can find the data from two different sources. So this is called, by combining this one, this is called join operation. So join operation is the most important operation in relational algebra and the database, relational database. So we have seen the union, intersection, minus, and Cartesian product. Plus, we are going to define the join operation. Join operation is, this is called the join. Join is same as what? Cartesian product plus selection operation. If you combine the Cartesian product and the selection operation, it will be join operation. So join operation, two input, two relation with what? Join condition. Okay. So have you ever heard about the join operation, join in database? Because somebody may be curious, why we need to join and join and join? Sometimes you need to join 3 tables, you need to join 4 tables, sometimes really 10 tables, like that. Why not combining? Then that is actually go back to the original problem. If we combine all the information together, it will be messed up. It will be slow to find the specific information. So because of that, Dr. E.F. could propose relational model. Only student information in student relation, student table. And only course information, only instructor information, only staff information, only professor information. Then we can easily manage such a data, very large data. However, it's very hard to access. So how to address such a accessing multiple source of data? Using join operation. We can use the join operation to access such a multiple source of the relation. Actually, this one is later called, if you separate the data, standardize the data, that is called normalization. So normalization is another process of the database design. specifically relational database design, very well, better the database design. Normalized means standardized, okay? So same meaning. So we will see such a thing later, normalization. But here, so keep in mind, so this is the set operation. This is the new operation, the join operation. So join operation need two input. And also, we need to define join condition. This one is called the join condition. So, join condition. Depending on the join condition, there are different types of join. First, if we are using the join condition like this, equality. If we are using the equality, so this one is called equijoin. So equijoin is the most simplest the join operation. So only access the equality. However, what if I'd like to join? So if this one is number, let's just assume the attribute is number and the SFN is bigger than IFN, like that. So if you are using the non-equality join, like this one, or even you can use the logical operation, true or false, any other types of the operation, so that is called the theta join. So theta join is the generalized join. Actually, when Dr. E.F. proposed the join operation, it's so actually equijoin. So because that's the idea, so we'd like to find the matched one. However, why not generalize? So we can apply the inequality. We can apply the true or false. We can apply any other operation that is a theta join. If we are using the like this, sometimes if your model is really perfect, okay, so we are going to use such a same name of the primary key, like the SSN. So intuitively, we understand Fn is same as the Fn. So everybody know it's the SSN is the SSN. So if we have the same name of primary key, same name of attribute, we are going to automatically join without the join condition. In this case, this is good example. We can actually without join condition. If you do not specify the join condition but join, that means it's a natural join. Naturally join with what? Same name of attribute. So at that time, to differentiate the natural join, actually natural join use the symbol asterisk. So for example, R asterisk S means this is not Cartesian product, this is not the normal join, this is called natural join. So from S, find the common name, same name of attribute, then automatically join. However, later, natural join is not actually popular. No relational database management system. No RDB use the natural join. Theta join is actually implemented in the relational the database management system. The Oracle Informatics did their commercial did theta join, but mostly popular the case is equijoin among the theta join. We don't use a lot such an inequality. We don't use a lot the logical operator, but the equijoin is the most popular one. Okay, so that is the join operation. All right, let's quickly move on. So the join operation is you can see when you combine two relations R and S with a join condition. This is a join operation. So this is really popular. I think because of join operation, relational database management system, specifically SQL, is the most popular one. So it's a think about the other program language like the C or the Python. If you have the multiple source of data, how can you combine such a data? You need to read the one file. You need to read another file and store as some the variable. Then for loop and for loop. Then it's a two-level loop. For loop inside the for loop, and then you need to do something. It's more complicated. However, in SQL, you can just using the one symbol, join operation. However, behind internal structure, behind the join operation, a lot of things happen. It's not actually simple implementation. It's a very, very expensive. Very, very expensive means a lot of computation. It uses memory access, it uses computation, it takes a time. So join operation looks very simple to use when you are using SQL. However, very, very expensive. You should be careful. So during the query optimization later, we will see how DBMS can handle such a join operation. There are different ways of the join inside the database management system. Okay. Is there any specific name of a symbol like this one? Join. So it's like a butterfly or something. But anyway, so this is a symbol used in the database join. Okay, so let's see the example. Suppose that we want to retrieve the name of the manager. I want name of the manager and of each department. So how can you get the name? Where can you get? So when you, this is like think about the first page of project. Query in English, right? So we'd like to convert this one into a relational algebra expression. So first, always when you create the relational algebra expression, first thing you need to do is find the source of data. In other words, find the name of the table, name of the relation. That is the first thing. So where can you get the name of the manager? Can you get the name of manager from department? Department does not have the name. Only manager, social security number. Okay? So name from the employee. So we need to access the employee definitely. Let's say the EMP. And however, employee does not have the information about the manager. Where can you get the manager of each department? Where? It's a department. If you go back to the relational schema diagram of a company, so manager social security number of department point the SSN in employee. So which means we need to access the department. First, list of all table or all relation name. Okay. Then next thing is find any condition. If you have the two relation, we cannot directly apply unary operation first. We need to combine. So let's take a look at which one can be used. Most of the case, the join operation. With the join, we need to merge. When you join, we need to what? The join condition. So among these, most of the case, we are going to use equijoin. So equijoin, so what is the, how can we combine employee and department? Using this information, name of the manager. So from each department, we can get manager SSN. Not always, but mostly, it's from the foreign key relation. If you take a look at foreign key, it can be used. Foreign key is kind of way to connect the other. Okay? Sometimes you can find your own way, but that's not always possible. But foreign key is always the way to connect. So if you remember, this is employee, this is department. So manager social security number, point SSN of employee, right? So we can use that. So SSN equal to manager social security number, right? So we almost done, not done yet. If you take a look at the requirement, retrieve the name only. First name, last name, and middle name initial. Let's say the first name, last name. How? Project. First name and last name. So this is the output result. So you can create a relational algebra expression easily. So you can see the department and employee. Manager social security number, SSN. The DPT on the manager is the result. It doesn't have the project, but you can put the project. Question. This one and the mine is different. What is the difference? Slide and on board, they are different. What are the different things? First, it doesn't have the project, so we can add the project here. What else? Order of what? Relation. Department, the join with the employee. Employee join with the department. Question. In terms of result, are they same or not? Same or not? Same. Okay. So this one and this one output are the same. However, something different. Yes.
It's being renamed to the department manager.
Oh yes. So we can rename the manager social security number. That's not a problem. And but there are different things here and here. Order of a relation, yes.
Order of the attributes?
Order of attribute. Order of attribute is still output. We can specify the project with this one. Then it will be the same. Primary key is also same because the results are the same. So when you really find this information, we have an employee room and department room. Which room you are going to visit first in this case? In this case, actually, from the last one, employee first. Okay. So employee, then department. This one, department first and employee. Any different things? So think about the extreme case. We have one department here. We have millions of employees, another room. So if you first visit the department, check the department, okay? Then I have the one department number and from the employee. So first come out the department number one. Then I can find this information. On the other hand, if I visit the employee first, okay? So we don't know. So first grouping, department number one, department number two, department number three, the whatever. Okay? Millions of people we need to grouping. Then visit this room, what's your department? Only one department here. Then we need to pick up the department number one group. Right? Which one is faster? Department first. So that's the idea of the query optimization layer. Okay, output are the same, but performance are different. So database, when the relational database access the data, there are a bunch of different ways. Okay, this is a simple example, but depending on how to access, in other words, depending on the route of such accessing the data, performance are really varied. Sometimes less than 1 second, sometimes several hours, several days it takes. So this one and this one is not different, nothing different in terms of output, but performance are very different. Okay. So that's the one thing. So this is a join condition. So we have the different join. So if you apply any condition of the join condition, it's called the theta join. Okay, like the inequality. So like the inequality we can apply. So natural join is if you have the common name of the from the both sides, you can apply that is the natural join, which is not very popular. So this is the example of the natural join. So when we combine we have the two tables, two relations, departmental DPT, project DPT, departmental location. Can you find any common name? NGR SSN, NGR SSN, right? So the other D name, yes, and the D number is different, the D number is the same. So using NGR SSN, the D name, we can join. So it's a natural join. Then we cover the most of the relational algebra operation. It's very simple. It's not huge. Okay. Then even think about the join operation. Join is actually what? Cartesian product and with the selection. When you implement, somebody asks you, why don't you implement this old operation? I need to implement the join operation separately? We don't have to. Instead, we can implement the Cartesian product and we can implement the selection operation. Then we can combine these two operations for one. So, which means when we actually consider the relational algebra operation, we don't have to implement all of this. Instead, select, project, union, difference, rename, and Cartesian product are minimal operation. On the other hand, if you need more operation, you can actually use existing this 1, 2, 3, 4, 5, 6 operations. So 6 operations are called complete set of the relational algebra operation. So it's a minimum. These 6 operations are very basic of basic. Then if you know that this one actually you can derive the other operation. For example, the intersection is not here, but intersection using complete set. So union minus and the union minus. Even, minus difference is here. So you can actually derive, create another operation. So these are the complete set of the relational algebra expression. What is the benefit of complete set? When you are going to implement, you don't have to implement everything. Instead, you can implement the first complete set of the operation. Operation in the complete set is a minimum. So you can use such a complete set of the relational operation. One more thing. So division. Division is not actually used a lot, almost no. But it's when Dr. E.F. Code proposed relational algebra expression, he proposed this operation. So using the example, the division is like the R divided by S. When we divide the one relation by the another one, so division means we try to get find from left-hand side. From the left-hand side, we try to find any tuple, any value that include all of right-hand side. So for example, in this case, when we divide R divided by S, so I try to find the SSN that include all of this, 1 and 2. So let's take a look at the ESSN, the first ESSN. 1, 2, 3, 4, 5, 6, 7, 8, 9 has the P number 1 and P number 2. So yes, so 1 through 9 will be returned because it has all the right-hand side. This means the PN. What about this one? 6, 6, 8, 8, 4, 4, 4. It's a 3 and no more. So this will not be. 4, 5, 3, 4, 5, 3, 4, 5, 3 has 1. 4, 5, 3 has a 2. So 4, 5, 3, 4, 5, 3, 4, 5, 3 will be returned. But the other, there's no 1 or 2. So division means, okay, division. This one is numerator, this one is denominator. So we try to find all numerator that include all the value of denominator. That's the idea of the definition of the division. So let's take a look at this example again. R divided by S. We try to find all R that include all of S. All of S means A1, A2, A3. So A1, A2, A3 in the B1. So B1 will be written. A1, A2, A3. So B2 is not. B2 has only A1 and A3. B3, A2, A3 only. B4, A1, A2, A3. So it will be written. Okay. So B1 and B4 will be written. So division is we try to find the numerator that include all value of the denominator. Complicated. So when people, the commercial vendor of the DBMS implement this division, they actually give up. It's not very popular operation, but it's a very complicated. It takes a long time to execute such an operation. So practically division is not used. However, sometimes we may need the requirement. Using other operation in the SQL, you can implement. So I'm not going to cover details, but just keep in mind the division may be possible, but division means, so we try to return all numerator that include all the denominator. One more example. So R divided by S. What will be the output of what is the T? B1, yes. B2, not. B3, not, because you know A1. B4, yes. So B1, B4. So that's the division. But if you implement this one in the DBMS system, it takes really, really long time. So we are not going to use this operation practically. Okay, so this is a summary of the binary operation: union, intersection, difference, Cartesian product, and the division. I'm going to skip this part. The next, aggregate. So I said Dr. E.F. Cote proposed the relational algebra, the model. 1969 and 1970 is proposed, published. Then, do you think it is commercialized right away? Actually not. He was in IBM, T.J. Watson Center, and IBM thought at the time, it's nothing new, so not worthwhile to commercialize. So IBM actually put more effort to another database. It's their IMS database and the hierarchical database instead of the relational database. So some of the people realized that this is a really good idea to manage the very large data, and they tried to implement his idea. So commercialized version released, and they start from something new DBMS system, which is called Oracle database. So, however, it's a funny story. Oracle, there's no version 1 Oracle database management system. They start from the version 2, version 3 like that, because usually if you see the version 1, what do you think? It's a new one. It's not, it doesn't look like reliable. So Oracle starts such a version 2, version 3, version 4, up to version 6. So from the version 6, it's commercialized and it's getting popular. It was 1980, upper 1980. It takes a really long time, almost 2 decades. So 1988, 1989, and 1920, and 1990, what happened at that time? Are you guys born? 1990, network, internet was getting popular. And also PC, the personal computer. So even I owned my first computer 1984. It was even before. It's really expensive. So my first computer I used, but it's not popular. There's no internet. Even though I need to use cassette tape, whether you guys know the cassette tape or not, it's magnetic tape to store the data because the hard disk drive is really small and the memory size is less than 1 megabyte, like that. But from around the 1990, so PC and such a computer price of computer is down and the network is connected. We need a high-speed internet. So we try to get such a benefit in the computing environment that's further 3-tier architecture. We don't have to put together. Instead, we try to get the benefit of a network. It's like the distributed, so which is called the downsizing. So Oracle also got the benefit of that. So they try to sell their product to the company. Then the people can use such a database. It's not only for the specialist. Okay, as in, if you see the SQL. Some of you guys already know what is a SQL, how to use it. Select from where. It's a very simple the program language. So when I joined the company, which was the bank at that time, even my company, the IT department, the employee for the SQL, like the analyst or the finance. And most of the such a headquarters employee, they try to learn how to use the SQL. Really. Then before that, if you get the report of the weekly report or monthly report, what you guys need to is first write down your requirement and get the approval from your manager. Then send the request to the operator and the code. And your operator send the sometimes punch card, and to the puncher, there's a specialist typing the punching and the hole like that, and submit. Then the operator run the program and print out to the output. Then the people, sometimes it takes 1 or 2 weeks to send out back to it takes a really long time. But using SQL, you can just type the select from where and get the report right away. So SQL was used for such a reporting tool a lot at that time, 1990 and even the beginning of 2000. Until we have very nice the interface, like the web application and so on. Until that time, the people actually employ non-IT, non-computer science. The people also use that. One of the reasons was the reporting. So it's a very nice reporting. But another reason is such a aggregate function. So think about why the Microsoft Excel is popular tool to organize, to manage such a number. It's provide very basic but powerful such a function like the summation. Easy to, you can drag and drop and sum. You can drag and drop and the average, right? So such an aggregate function, statistical function is still popular. So SQL also the relational model, provide idea of the aggregate function or statistical function. What kind of a statistical function you know? Any function used in the statistics. Sum, summation, and others. Average. Count. Right? And others. Standard deviation. Variance. And such a statistical function. All of these are implemented in the SQL, the relational algebra operation. So these are called the aggregate function. But think about, so this is the one example. I'd like to count number of employees per department. Right? Department number 1, 10 employees. Department number 2, the 20 employees, like that. How can you count such the per department? In real the example. So we have the employee with the D number. So I try to count How can you count? We need to first grouping. Okay? We need to first grouping. So group number 1, group number 2, group number 3, like this. Then count. Same thing for the average. I'd like to get the average salary per department. Per department. Group number 1, department number 1. Group number 2, department number 3. Group number 3, department number 3. Then apply average. So such an aggregate function always work with grouping, which is called the group by grouping. Group by department, group by last name, group by something, group by major. You need to group. The problem is also this one, group by. How can you group? It requires sorting. Sorting is one of the most important the data structure in computer science. Why? It's really expensive. Whenever you sort the data, it use two things: computation, also space, memory space. That's the two things. When you measure any quality of the data structure, linked list, the hash, whatever, in your the basic data structure class, so you always analyze such a data structure, two things. So number of access and the space in terms of big notation. Do you remember that? But sorting is one of the most expensive operation. So we need very fast, efficient. So later we will think about this one. So anyway, to group by, to calculate this, we need to grouping. That requires sorting. So we are going to define the relational algebra expression like the for aggregate function. It's like the F. Yeah, I guess the Greek letter of the capital letter F. Then this time, so any grouping factor is a right-hand side. For example, per department, I'd like to count number of employees per department means D and O is here. I'd like to average score per grade. Grade will be here. I'd like to standard deviation per class will be here. So grouping factor, which is called a grouping factor, is the right-hand side. Left-hand side is your aggregate function, like the average, the count, summation, and any other. So left-hand side is the aggregate function, right-hand side grouping factor. So let's take a look at the example. Again, definitely it needs the relation. Input is also relation. So let's take a look at the example of the such aggregate function. It's my mistake. Sorry. The grouping factor is left-hand side. And aggregate function is the right-hand side. For example, DNO or the class, such a grouping factor left-hand side. And this one is function average, salary, average, the count, or the standard deviation. Such a function is the right-hand side. Let's take a look at this example. This one. What's the meaning of this? Number of employees. So specific number is the primary case, so we can count. Number of the employee and average salary per department. Okay, from the employee. So this is the aggregate function. Output will be like this. If you run this one DNO and the count 10 employee and average salary is 30K. Department number 2 and count 5, average salary is 15K. Like this. Also, it will be sorted automatically because you already sort by the grouping factor. It will be sorted like this. This is the output. So we can apply any aggregate function like the count, average, summation, standard deviation, variance, so any such the statistical function can be used. However, if you go back to here, there is no left-hand side, right? Grouping factor is not specified the left-hand side. If you leave the blank for the grouping factor, we consider input as the one group. That means we can even use who is the employee? The most salary, maximum salary. With grouping factor is not specified, so we can use the input as the grouping factor. So we can use the maximum, minimum, like such a aggregate function. What about this? This one is the minimum least salary employee. This one is total salary in the employee. Not we are going to regard the employee as the grouping, one group. Okay. So then we can use such a thing. What about this one? So it's the employee count. So this is an example of this one, the D number, count, and average salary. But in the real implementation, it will be automatically sorted. Okay, 1, 2, 1, 4, 5. Okay, so then I'm going to skip the recursive, instead the outer. I think that this is the last one, 2 minutes. I think with better, this because it's a little bit time. I need a little bit time. I'm going to cover the outer join with the example next class. But before we end, so one last thing. So anyone who ever used the C chord before? What is the most popular syntax of the C chord? Select.
Select from star.
Select. And next. From. And where. Right? So I think you probably heard about the select from where. It's really popular. Let's think about the select from where with this one. So this one is a selection. Selection is the condition. So when people implement this relational algebra expression to the C chord, selection is implemented in the where condition. So selection. Then projection. What about the projection? Projection is implemented in selection. So you can list up the column projection. You can list up. What about the rename of the relation? This one is implemented in front. It's a as. It's an alias. You can rename the table name. It's an alias. And what about this rename? It's the rename of what? Attributes, column. So this one also can rename as is also alias. What about this? This table name. Table name definitely goes to front, close. Okay, then what about this one? So these three, union, intersection, minus, difference is you can use the union. You can use minus. You can use intersection. with another sequence. Like this. What about the Cartesian product? Cartesian product is from join without condition. So if you remove the condition from the join condition, then it will be automatically Cartesian product. What about join? Join is implemented to the where condition. So actually, where include two parts, selection condition and join condition. But in SQL, it doesn't specify which one is a selection, which one is a join. Instead, it's the same, it will be connected to the AND or so such a the logical operator. Then, what about the grouping factor, and this is the everyday function. So every function can be applied to the directly column, okay, or attribute name. And this one is a specialized one, so we can use additional one, group by. With heading, we will see the details of that. Okay? Then actually this is the syntax of SQL. We don't have to learn the SQL separately. We almost cover SQL based on relational algebra. One more thing. Sometimes I need to order the output, okay, from the increasing or decreasing. So at that time you can use order by ascending, descending. Everything. This is the 90% of the syntax used in the SQL. Mostly, this is enough to do any kind of the SQL. So SQL is kind of actually implementation of this relational algebra. In other words, if you understand clearly relational algebra and relational algebra expression, SQL is not very difficult. A little bit the details of syntax, you can follow that. And also, depending on the commercial vendor, like the Oracle has a slightly different from the Infomix. Infomix is different from the other in implementation. Otherwise, they are the same. So it doesn't matter whether I learned the SQL using the MySQL, but I never use the Oracle. That doesn't make sense. It's the same thing. Okay? So if you learn the SQL or relational database with any DBMS, it's totally fine because they are following the same standard, same the foundation. Okay, so next class I skip the type of the outer join. So I quickly go over the outer join, then start the SQL part. But I already explained the SQL. So before that, I'd like to give the several examples of the relational algebra expression like this, how to create the relational algebra expression from the requirement. That is the part of the page 3, right? So page 3, page 2. Anyway, it's part of the project. Okay, then I will give the homework. I will give you the homework on Wednesday. At the end, there are a couple of the examples. I will explain. Any questions? So Wednesday, we are not going to start the lab. Instead, I'd like to cover the SQL part and the remaining of the relational algebra. Okay, thank you, and see you on Wednesday.